Hello, and welcome to What's the Cost of a Millisecond. My name is Avishai Shalom, I'm a developer advocate at ScyllaDB, and I'm Nukenberg on Twitter, look me up. So what is ScyllaDB? ScyllaDB is the company behind the open source NoSQL database Scylla, which is a high performance database that's API compatible with both Apache Cassandra and DynamoDB. Do check it out. It's open source. We also have enterprise version with support, and of course database as a service, your cloud. So look it up if it's interesting to you. But of course we're not here to talk about Scylla, so let's move on to talk about latency amplification. So what is latency amplification? Let's take this diagram, for example. This is basically a system that has, two services, A and B, that talk to each other. A basically executes a sub request to B, and also has a database. And if we sum up the latency of each processing stage, we would get to something like 16 milliseconds, right? So, of course, the answer is no. Otherwise, why would I be asking this? We would get to something that's much, much higher, something like 740 milliseconds. How's that possible? The reason is because of latency amplification, and you actually have latency amplification at every stage, as you can see, from a bunch of different reasons, which I'll go into in this presentation. So what's happening here? Every queue along the way, and everything in the system that has a network or some kind of shared resource has a queue. And every queue amplifies the latency. And of course, if you hit a timeout because you're unlucky, it has a very large penalty. And then you have to retry, which also is going to take some time. And all of this compounds. So at every stage it compounds even more. And also transactions impact each other. So it's not like if you hit the timeout, then only that transaction suffers. All of the transactions are going to suffer. We're going to talk about this in a bit. So the problem is that to understand latency amplification, we have to understand queuing. So I'm going to give you a really fast crash course in queuing theory. It's a very large topic. I've talked about this in a number of different places, and also a lot of other people talked about this. There are university courses, books, whatever you want. So I highly recommend that you look for good resources on queuing theory. But this is the basic model. So what we have is a service center, and this service center is being serviced by a queue. Basically, it takes work out of the queue, and the queue is kind of a buffer or storage for incoming work. It goes into the queue, and then the service center takes the work out of the queue. And the question is how long we're going to wait in the queue, because the latency that we observe is basically the time that we wait in the queue plus the time that it takes the service center to service that request. So the time that it actually takes to work on that request. So this is what queuing theory is about. It's about understanding or in computing how long we're going to wait in the queue and how long it's going to take, what's the size of the queue is going to be, and so on, so on, so on. And the problem is that we have something called head of line blocking. So different tasks take different times to complete. It's not uniform by any way, and one task might be larger than other ones, or maybe at a certain point the service center is going to experience something like a garbage collection, or maybe talks to some backend that has non-uniform latency. Let's say that the database you hit P99 of the database, whatever, doesn't matter. And the service center might be blocked for a while, and then what happens is that everything in the queue is going to wait for the head of the line, basically the head of the queue, to be unblocked. So when this happens, we say that the tasks in the queue are experiencing head of line blocking. And this means that a single task that is getting delayed for whatever reason is going to cause all of the other tasks that are waiting in the queue to be delayed as well. And if the queue is long, it's going to impact a lot of other tasks. And this is really the bad news for the latency high percentiles, because even one P99 of the backend is going to cause a lot of other tasks to experience that latency as well. So it's going to translate to not P99, maybe P95 even. So it's going to make your even lower percentiles worse on the next stage. So not good news. So This is a simulation of a queue. This is the MM1 model, a simple queuing model, and basically assumes exponential distribution for the service time, the time it takes to service a request. It's plotted on the top left, and Poisson distribution for the arrival rate, the rate at which new work is being inputted into the system. So none of those are uniform, of course. Those could be a bunch of different distributions. In your system might be something else, but this is not really the point. All the queues behave in similar manner, and this simulation uses those distributions. And the thing is that sometimes you get 10 requests per second. Sometimes you get 20. Sometimes you get close to 0. It varies depending on the distribution. It's not uniform in any way. And on the bottom, you can see a microscopic view of the queue. Basically, we have plotted the length of the queue on different times. And what you can see is a very interesting phenomena where the queue is almost always either almost empty or completely or full. Basically, it has a spike of backlog. So why does this happen? This happens because a queue is basically a lose-lose situation. If for some reason you hit a slow task and you have head-of-line blocking, then you're going to get a buildup of the queue very, very fast. Or maybe for some reason you had a spike in the arrival rate and you had a bunch of tasks that get in the queue at, around the same time. Then you're going to get the buildup of the queue, and that's going to happen very fast. But if for whatever reason the queue is empty and the service center cannot get any more work, then it's going to sit idle and it's not going to do anything, and we can't save that time for later. So if we get delayed, if there's a backlog on the queue, we get screwed up basically. And if for some reason we're ahead of the throughput, then we lost the time that the service center set and did nothing. So lose-lose situation. That's basically the problem. This happens because of the variation in service time and arrival rate. And this is very important to remember. So this translates to this latency curve. This is a plot of latency, or actually latency amplification versus the utilization of the system. So utilization is the arrival rate divided by the service rate. And basically it means that if you have 5 requests per second arriving and the service center can process 10 requests per second, then you're going to have 50% utilization, or 0.5, and you get the idea. And as you can see from the graph, the closer we get to 100% utilization, the higher latency is going to be, and it rises in a non-linear fashion, which means it rises really, really fast as we approach 100% utilization. So this means that we need to have overcapacity, sometimes a lot of overcapacity, in order to have decent latency. How much overcapacity? It depends. It depends on the variation of the service, of the service rate and the arrival rate. It depends on the time, on how slow the service is, and so on. This is the Kingman formula. I'm not going to dive into the formula. What's important here is just to see that the wait time, the latency, is proportional to the variation coefficient squared. So it's again rising in a non-linear fashion. So I have a nice tool called Cumulator to demonstrate this. And basically this is the same latency curve that we've seen before, but now I can actually play with the coefficients. So if I make the variation higher, doesn't matter if it's the service rate variation or it's the arrival rate variation, as you can see, the latency curve becomes worse and worse, which means that we get higher amplification even at lower utilizations. And similarly, if utilization is going to be better or worse, we're going to see the latency curve changes accordingly. So this is basically the problem. The higher the variation is, the worse our latency curve is going to be. Tasks, we imagine them to be independent. So if we think about, some task that had a problem or was slower or has a bigger payload, bigger JSON or whatever, doesn't matter, we tend to imagine that it's not going to impact other tasks. But as we've seen, head-of-line blocking, there is cross-task impact. And every shared resource has a queue. A lot of things that we don't think about as queues actually are queues or behave in similar amount of queues. Of course, every resource like disks or CPU, but also thread pools, load balancer, connection pools, locks, database locks, sockets, whatever. They all behave like a queue, and they are going to cause cross-task impact. So this is very unfortunate for us. And if the variance of our service is high, it's going to make this effect a lot worse, because it's going to make queuing worse. So we might think that we can separate queues for service centers to make this effect not as bad. But unfortunately, this has some side effect of lowering the utilization of the system, and of course the throughput and latency. And if you want to understand more about this, then I suggest that you learn more about queuing theory. So, to give you an executive summary of queuing theory, if you're going to have high utilization, you're going to have a lot of latency amplification, and it's going to happen in a nonlinear fashion. The closer you're going to be to the edge of your capacity, the higher latency amplification is going to be. If you're going to have high variance, again, you're going to have high latency. So try to have low variance. And shared queues, they are going to have higher throughput and lower latency, which is why we usually have one checkout line in supermarkets. And of course, I'm talking about identical service centers. I'm going to touch this in a bit. And most important thing, never ever use unlimited queues. Why? Because as we've seen for head-of-line blocking, the longer the queue, the bigger the effect of head-of-line blocking is going to be. So if you have 1,000 items in the queue, the last item is going to have to wait for all the items in the line to be cleared before it can get serviced. So it's going to have a huge latency. So in order to limit the impact of those kind of things, we have to limit the size of our queues. So this is basically everything you need to know about queues for this presentation and in life in general, but do read more about queuing theory. So now that we understand queuing, let's talk about sources of latency amplification in our systems. So of course, we talked about queuing, but we haven't talked about the fact that queues are everywhere, basically every shared resource, and a lot of other things that we don't think about, like event loops. They also have a callback queue, and of course queues like Kafka or RabbitMQ or queues in Java or whatever. And the problem with queues is that they're often not monitored. In a lot of drivers, a lot of asynchronous things that have a thread pool or some kind of a queue, it's not monitored. We don't know what the queue length is, and of course we don't know what the latency amplification is unless we try and measure it. So this is where awareness is required, so we actually measure this. And remember that utilization also fluctuates. So if you are running at 50% utilization, and for some reason you have a 10% increase in utilization, it's going to take you from 50% to 55%, which translates to about twofold increase in latency amplification. But if you're running at 90% utilization, a 10% increase in utilization is going to take you from 90% to 99% utilization, which is going to increase your latency amplification by a factor of 10, if not more, which is like horrible. It's basically an outage. So it's very problematic when you're running near the capacity limits of your system. Timeouts. So timeouts is something that we need to have. Basically, we're going to break or stop or cancel a task when something takes too long, or maybe it won't complete because we lost a packet somewhere. Doesn't matter. The problem is that timeout values are often arbitrary. How do I know they're arbitrary? Because they are too nice. If you look at the number and it's 1,000, there's no way someone measured this. Numbers that you measure are never that nice and that clean. It's usually something like 2.7. It's never 100, right? So most of the values that we see are arbitrary, and they're way too long often. Even the default numbers. So for example, Hikari CP, a very popular connection pooling library in Java, has an acquire timeout. For acquiring a connection, it has a minimum timeout of 250 milliseconds. Now, it takes much less time to open a new connection to a database these days. So that number doesn't make sense. You can think about other things like timeouting the cache. If you have a database that takes 20 milliseconds to respond, it doesn't make sense to wait for a timeout of 100 milliseconds from Memcache, does it? And yes, I have seen this in the field. So remember that every time you're waiting for a timeout, you're hogging important resources. So you don't want to have this timeout too long. And of course, if your transaction failed, then you might need to try again. And the problem with retry is that it takes even longer to try again. And if you try multiple times, it's going to take you longer and longer, especially if you have long timeouts, because even the retry can take up to the timeout to complete. So that's kind of a problem. If all of those retries have the same timeouts, and this is something to remember, do they all have to have the same timeout? Usually it makes sense to have a shorter timeout for the retry for this reason. Fork join. If you have a job that forks off a couple of subtasks and it waits for all of them, this is the case, for example, with MapReduce and stuff like that, then you're going to wait for the last task to complete, which means that your latency is going to be bound to the higher percentiles. And I've plotted here what the probability of hitting at least one high percentile, P99, P95, P999, what the probability would be, depending on the number of tasks. And as you can see, for the 95 percentile, even with a small number of tasks, there's very high probability of hitting at least one of them. So this means that fork join is going to increase your latency by a very large amount, very fast. And of course, deep stack kind of behaves like fork join, because it's a sequence where you have to wait for the entire sequence to complete. But it's actually worse than that, because unlike fork join, where we wait for the slowest task, here we actually have the latency amplification compounding, and it's compounding multiplicatively by multiplication. So it's actually going to be a lot worse than fork join. So how do we combat latency amplification now that we understand the problem? First thing that we can do is proper timeouts. How do we have proper timeouts? Just measure. Chart your distribution and then your latency distribution, either using percentiles or histogram, and determine the correct timeouts using that maybe percentiles. So by definition, P99 means that 1% of transactions are going to be more than this, and if you set the timeout value to the P99, then you know that only 1% of your transactions are going to fail due to timeout. And of course, if you are not willing to accept 1% of failure, then use the 99.9 and so on. Basically, it allows you to tune between the latency that you're willing to have, maximum latency that you're willing to have, and the failure rate that you're willing to have. So use a histogram of percentiles to do this. And you can compare this with the failure cost. If the cost of failing is high, then you might want to wait longer. If the cost of failing is low, then you might want to wait less time and maybe retry. Remember, the timeouts don't have to be static. In many cases, people just measure once and then put this number and then never change it. But you can actually have dynamic values. Why not look at the time window of the last 5 minutes and take the P999 of that and use that as a timeout value, or use lower timeouts when you have high load and you want to evict resources faster. You get the idea. You can play with this in a number of interesting ways. A very cool pattern for this is timeout budget. Basically, the idea is that you have a global latency budget or a timeout for the entire request in your stack, and you pass the remaining budget on the request context. Usually you need some protocol support for this, and on every processing stage you decrement the time that it actually took to process the request so far from the overall budget, and then the timeout would depend on whatever budget is remaining. So this is nice for two reasons. If, for example, I don't have enough budget remaining to execute the rest of the tasks, I know that tasks might take, let's say, 100 milliseconds, and the budget is only 50 milliseconds, then I can abort early and release resources. On the other hand, if tasks took shorter time than usual to complete, it means that I have more time in the budget to wait for other tasks and increase the timeout for whatever is going to happen next. So it's basically a win-win situation. It's a very cool pattern if you can use it. Parallel dispatch is another nice way to lower latency. Basically, the idea is to fork multiple tasks in parallel and wait for the first answer. So if we have identical queries, then it doesn't matter which one of them completes. So the problem with double dispatch that it costs twice. It's going to cost twice the network throughput, might potentially tie up two servers to answer the requests, and so on, so on, so on. We can also do speculative execution, get data before we need it in advance, or we can do some kind of branch prediction. We can guess that we might need some data and get it in advance and just throw it away if we don't need it. Or there's another interesting pattern that's called harvest and yield, which combines a bunch of those, which means that we can ask in parallel multiple shards of data, and for each shard we can ask multiple replicas, and then wait for a deadline, and when the deadline arrives, then we proceed with whatever answers we got, and then we can tune on the completeness of answer and the latency that we're willing to absorb. Read about this more online. It's a very known pattern. Retries. We can have smarter retries. We don't have to have static retries. We can have speculative retries, for example. This is something that is being used in the CQL drivers for Cassandra and Scylla. So the idea is it's similar to double dispatch, except it's slightly cheaper. We basically have two timeouts. One shorter timeout for retry, which means that, for example, if we execute the query, and then after 5 milliseconds, if we didn't get an answer, we execute the retry, even though we haven't failed the original query. And then we have a race between the original query and the retry, and we use whatever is going to complete first. And the overall timeout might be 100 milliseconds, doesn't matter. So it's a little cheaper than double dispatch, because most times the original query will complete before we execute the retry. But of course you need to have idempotent APIs for this, which is also true for whatever retry pattern that you have. You need to solve this data problem anyway. So, just putting it out there. The second retry can have shorter timeout. It usually doesn't make sense to have the same timeout for the retry. A good way to do this is combine this with timeout budgets, for example. And you can also use probabilistic retries, which means that you can make an educated guess about the probability of the backend answering to the retry. If you've noticed that you have a lot of failure rate, there's no point in retrying, because probably the server is not going to answer anyway, and every retry is going to increase the load on the backend. Most important thing when we're talking about queuing is capacity and latency management, because as we've mentioned multiple times, the higher the utilization of the system, the more queuing you're going to have. So first thing to do is to limit concurrency, and according to Little's law, highly recommended that you read about this. Cap the queue length. I've mentioned this a couple of times. The shorter the queues, the lower the latency penalty is going to be. Yes, you might have errors, but that's a good thing. This is basically protection against overload. The slower the service you have, the lower utilization it can have. So if I have a slow database, I'm going to have to run it with lower utilization, basically more overcapacity. If I have a faster database, then relative to the rest of the system, of course, then I can run it with higher utilization and have less overcapacity. That's a general idea. Again, learn more about queue theory. If I have high variance services, they need to have lower utilization and higher overcapacity. You get the idea. Back pressure, back pressure, back pressure. If you don't know what back pressure is, highly recommend that you read more about this. Basically, the idea is that we propagate from the bottom of the system to the top of the system the fact that we have overload. If we have something that's overloaded at the bottom of the system, there's no way for the load balancer to know about this. It's going to keep stringing traffic inside the system and overload the rest of the system. So we need to somehow communicate to the edges of the system that we're experiencing overload inside. And this is basically what back pressure is. We're notifying, backwards, we're applying pressure, and telling it, I can't take it anymore. And then, the rest of the system is doing the same. And then when the edge knows that we're overloaded, it's going to do load shedding and basically reduce the load on the rest of the system and allow it to stabilize. So again, highly recommended that you read more about those patterns. Reducing variance. This is something that really helps when we want to raise utilization and lower our latency amplification. So one of the most useful patterns out there is separating systems and services with different latency characteristics. In a lot of cases, you see servers that are servicing very different transactions that have very, very different latencies, and this basically increases the overall variance of the server. So you might want to consider to separating those two different transactions into different microservices or different servers, so they have low variance independently. This is very useful and actually solved a number of performance problems, so you might want to look it up. And the reason why this happens is basically the semantics dynamics trade-off. Think about SQL queries or a programming language. It can do anything, and because it can do anything, it means that you're going to have high variance on performance query. One query is going to take much longer because it's more complicated, because you can do anything. So the simpler your service is, or your API is, the better performance variance you're going to have. And the more complex API or more complex interface you're going to have, the worse your variance is going to be. So just design your API with caution. You can't do better than your backend. You want to have a fast backend and a backend that has very low variance. If you have a database or whatever backend that has very high 99 percentile or 95 percentile even, then of course you're going to have high variance for the service. It can only be worse than this. Similarly, for garbage collection and things that don't have quality of service because you don't have preemption, think about Node.js, think about Golang. You basically have to do this yourself. You need to make sure that you yield, that you allow the scheduler to service other tasks, or you break your transaction into small tasks. And if you have garbage collection, you want to reduce it as much as possible. And remember that you have other asynchronous tasks out there that might also increase your variation. So just be minded of this and reduce this as much as possible. So to summarize, what's the cost of a millisecond? It's much, much higher than you think. I've seen cases where a single millisecond at the bottom of the stack has translated to an increase of even 10 or 20 or sometimes 50 milliseconds, definitely on the 99th percentile. So it's worth remembering that you're actually interested in percentile curve. We don't actually care about averages because they don't tell us much when it comes to latency, and they definitely don't tell us much about how much amplification we're going to have. And the high percentiles, especially at the bottom of the stack, are going to have disproportionate impact on the latency penalty that the rest of the transactions are going to have because of head of line blocking and all the stuff that we've shown. And if you have even a single millisecond increase at the 95 percentile of the lowest part of your stack, it's going to translate to a huge increase, definitely on the P99, but also on even the median or the mean latency of the top. Latency amplification is one of the worst problems in system performance and one of the most common reasons for systems that run at very low utilizations from my experience. And this means that we need to actively combat latency amplification and reduce it in our systems everywhere. So thank you very much, and if you have any questions, then you can catch me later in the chat or on Twitter, and I'm happy to answer your questions.